My name is Tony Davis. I'm the Vice President of Technology at RealD. And I just wanted to thank everybody here so much. The 30 years is a fantastic milestone. And what I wanted to talk to you today a little bit about is where did the technology go that you all have been developing? So what's happened with 3D and what's happened with 3D in cinema? So certainly 3D generally, or stereoscopic imaging generally, has been a big market in all kinds of places. But one of the big successes has been stereo imaging in movies. And so we've, at RealD, we say thank you to all of you. And we want to show you a little bit about what has happened and where we're going with this. So the first thing let's talk about, this is the elephant in the room, what's going on with 3D in movies? And the answer is it's still doing pretty well. So if you look at all box office in cinema, about 53% of the box office is going to be movies that are 2D only. And so the rest of it are movies that are available in either a 2D or a 3D format. And if you look at that, 26% of the box office is movies that are available in 3D, but people are watching in 2D. So 26% is the 2D portion of 3D movies. 21% is the piece of the pie left that people are watching 3D movies in their intended format, in 3D in movies. So what does that come to? That's about $8.2 billion in overall box office of people watching movies in 3D. And of that, about $1.5 billion is the incremental upcharge for people to watch a 3D movie. So there are people out there who really want to watch a 3D movie, and they love going to the movies and watching this in nice stereoscopic display. How many people are there that like that, though? Well, we have numbers because we care about these people. So we have 24% are very 3D interested. These are avid people. These are my people. These are the people who always want to watch a movie in 3D if it's available in 3D. They will go and pay that ticket upcharge, and they will sit down with the popcorn, and they will love a 3D movie. We have 23% who are somewhat 3D interested. They like 3D movies. They're not going to go seek them out. They don't necessarily drive extra far to go see it, but they will enjoy a 3D movie and aren't turned off by it. 33% are 3D interested, and this is the most flexible region of this. People who are interested in 3D, they'll go if their friends are going to see a 3D movie. They're not going to seek it out. Specifically, if there's a 2D and a 3D movie available at the same Cineplex, they're going to choose the one that's better according to their time frame. And if there's a little bit of hype for the 3D movie, they'll go see it. Otherwise, they're like, no, I'm fine with the 2D movie. 20% of viewers will not see a 3D movie if you pay them lots of money. They hate 3D movies. So there are 20% of people out there who will never go watch a 3D presentation. And those are not our audience. We're not going to try to convince them to go see a 3D movie. They don't like it. So that's fine. We have another good group of this pie that we can go work on to make their experience better in one way or another so that they will watch and enjoy a 3D movie. So it's really on us to make sure that what they're seeing is good, it's compelling, it's something that they want to do, and they feel like they've really got their money's worth for that 3D upcharge. So what do we work on? So we work on a lot of technology. We're working on something we call a cleaner canvas, making the canvas that movie makers use cleaner and nicer, and we want a broader palette, something that they can make more, bigger, better movies with, so that it's something that they can really go enjoy. And this is on the set of Hugo, if you recognize that clock tower and things like this. So there are people who really, filmmakers who love making stereoscopic movies. So what do we work on at RealD? Well, we work on things kind of from end to end, all the way from camera to people watching things. So we care about all kinds of artifacts that happen at the beginning, and then we care about what happens in the movie theater itself. So let's start at the movie theater, actually. We'll start at the other end of this thing. So this is where most people know us, if you know us at all. We're known for what goes in the theater. We have the image encoding technology. So this is the system that actually does the 3D, the circular polarization coming out of the projector. We have eyewear. We are the largest manufacturer of eyewear in the world. We've made over 2 billion of those little glasses that have gone out there. And then we have screens, and this is something that's fairly new. We've been working on our screen technology, actually polarization-preserving screens. So as a refresher for anybody who doesn't know how our systems work, our systems are light recycling systems. And what that means is the light comes in from the projector randomly polarized. And what we do is we split it between vertical and horizontally polarized light. Normally what you might do is you might throw away, if you have a normal polarizer, you're going to throw away about half your light at that point. But we don't throw it away. We use either a wire grid polarizer or something similar to split this light. And then it goes to two different paths. One path we're going through, and we have a liquid crystal that's going to circularly polarize this light, make it clockwise, counterclockwise polarized. The other path goes through a polarization rotator to fix it to the correct polarization, and then we also send it out. So if you see one of our systems in the theater, if you're me, you walk into a movie theater, the first thing you do is you turn around and you look at the projector to see what do they have back there. And if you see what looks like two beams of light coming out of the projector, they're not a left and right eye. They're actually both the same eye at the same time, but one is the light recycling path that's going through there. And so they're both coming out clockwise or counterclockwise. It's switching, of course, back and forth 144 times a second. We have a lot of different systems. This is just the way we have these things for different throw ratios. So throw ratio is the ratio of the width of the screen to the distance of the projector. So when we talk about narrow throw ratios, like in this room, we're running at a fairly narrow throw ratio. So it's with respect to how far it is to that projector, the screen is not very wide. We can put about 5 of those screens before we got to the projector. So something like our original XL system, which came out around the time of Avatar, which is about a 1.45 throw, so it's used for more narrow throw applications. As you get to wider throw, it's harder for us to make optic systems that can cover that entire throw area, and so we have systems that go up to very wide, kind of very immersive screen situations. So let's talk about our newest one of these. I'll just show you what our newest switcher looks like. We call it the Ultimate 3D because our marketing group is paid to make up these names. They're paid way too much. So the Ultimate 3D has best-in-class efficiency, very high stereo contrast, so we don't want very much light leakage from one eye into the other. It's got better high dynamic range quality. That means that we don't want light scattering from one side of the screen to the other. And we can go to immersive throw ratios. This is a 3-beam system. So anybody who's familiar with these systems, they come in 2-beams and 3-beam systems. The nice thing about this is you keep the as you're splitting the image up for light recycling, you keep it fairly close to the main beam, and so you have less keystoning issues and things like this, but you also can have better optics in these other paths because they're fairly small, and you have better optical performance. And people who run theaters love this. They're like, oh, how do I align all these things? Well, there's a little web app, and you put on there, and you drive your images together. I will say that this isn't necessarily the most interesting thing, but it's a lot of fun when you do it on a 70-foot laser projection screen and you stand there with your iPhone moving the screen around. You feel very powerful. Okay, so screens. We have what we call the ultimate screen. What is the ultimate screen and why did we start making screens? So this is a standard silver screen, and we've need for 3D in theaters. We need a polarization preserving screen. And that's usually been a silver screen, and it's a very old technology. This is how a silver screen is made. There's a gantry, robotic gantry, that's got this big sheet of vinyl that's hung up there, and this gantry goes up and it sprays what is actually aluminum flake onto the screen. You don't have to sit around and watch this happen, but it probably helps. This is what a micrograph of that silver screen looks like. And you can see all of these little flakes of aluminum all in there. And you can see a couple of problems with this. First is all of these little dark areas. These are little crevasses where the light goes down in between pieces of aluminum and doesn't ever come back. So this is where you just lose light down into here. The other problem is all these sharp edges. Those sharp edges are very bad for polarization preserving. They tend to knock our polarization into the wrong state. So the light output from a screen like this isn't really great. One of the things about a screen like a silver screen is it is supposed to be a gain screen. That is to say that it's not Lambertian. It reflects most of its light back in a particular direction from which the light came, and that's very important. So you have a gain of 2 or 3 on a silver screen, but hidden in that is a loss of about half your light. About half your light is being lost down into these crevasses. This is an ultimate screen. This is our screen. So the RealD Ultimate screen is an engineered screen surface. It's much more like a Mylar balloon. So imagine that I had a sheet of Mylar strung up here. What you would see is a mirror image of the rest of the room. You'd see what I'm seeing. You'd see the projector back there. It would not be a very good screen. But then we put these very small kind of coral-shaped pattern into that screen, and that does the diffusion that we need. So it actually turns it into a movie screen. But our screens are extremely reflective. They are essentially a first surface mirror that's got little wiggles in it. And we have about 91% reflection efficiency off of that screen with very high stereo contrast preservation. And we can make it in a variety of different gain curves. These are gain curves, as shows this angle of reflection and how much light you're getting. And so a gain 2 screen gives you a gain compared to a Lambertian surface. And then you can go up to a 3.8 gain, very high screen. But what you want is something that's extremely wide. And so we can make something that has a very, very wide, so we don't put all our light into the gain per se. What we're doing is putting it into the width of this gain profile, so that rather than having a little hot spot in the middle of the screen on a high gain screen, you now have something that's much broader and much more visually appealing. So how do we make a thing like this? Well, we essentially print it. What we have is a substrate goes past a roll with our engineered pattern on it. We put a UV resin in there and cure it, and that's how we produce the pattern. And then we sputter aluminum on top of that. And so this is how we make this reflective. We then laser perforate it for sound, because the speakers are behind the screen. And normal perforations in silver screens are fairly large. They're about 1 millimeter in diameter. And you can actually, you sit in the front row, you'll see those things, and they can be quite irritating. So ours are extremely tiny. Those are our perforations that we have there, and we have the same audio transmission through the screen. And also, since the amount of the total area that we are losing to holes is much smaller, we also have more light from that. And so we're looking at how much light do we really end up with. We start with, if you have a Pearl 1.8 screen, this is a standard silver screen, and you lit it up to about 14 foot Lamberts with more lamp power, and you compare that to our 2.0 screen, we both hit 14 foot Lamberts on center, but what's going to happen is visually we're going to have a much larger illuminated area that looks nice and bright. The stereo contrast is also dramatically improved. Stereo contrast of a typical silver screen is about 100 to 1. And it's important to remember that preserving circular polarization off a screen is about twice as hard as preserving linear polarization, because a double reflection will preserve the direction of linear polarization, but it will flip the polarization of circular. So circular polarization preservation is very difficult off of a screen. Ultimate screen, we run usually about 350 to 1 stereo contrast on center, and we do that over a much wider area as well. So if you put all these technologies together, if you took a kind of one of our a standard absorptive polarization system and a standard silver screen with a given projector, you'd be at about 8.5 foot Lamberts. We are old-fashioned in cinema. We do foot Lamberts. We've done foot Lamberts for 100 years, and we'll do it for another 100. So so just to stay with us, it's going to be foot Lamberts. 8.5 foot Lamberts on center. If we use the same projector and a light recycling system and an ultimate screen, we'll have 24 foot Lamberts on center. And it's very important, the audience perception of 3D is dramatically improved if the light goes up. If you go to a cinema, everything is supposed to be 4.5 foot Lamberts. That's the standard for what you're supposed to be seeing after glasses in a theater. I'm not going to tell you what you really see, because that would be mean, but it's not usually 4.5. Come and buy me drinks or something, and I will tell you everything about where you should watch your movies. But until then, I'm not saying. So it is a cleanable surface, which is something a silver screen can't do. If you touch a silver screen, you damage it. And our surface is much more robust and reliable. It's a fairly rigid surface, so you can actually vibrate it to do laser despeckling. It's not as rigid as the beds in this hotel, but it's pretty rigid surface. And you can wiggle it with magnets from the edges and do laser despeckling. And we've been installing these systems. These are fairly new, so we don't have that many out there. We just passed 100 screens installed worldwide. We're starting to put them in more places. In the United States, we don't have as many. There are only a couple of, 3 screens in the United States that are actually in commercial use. Most of these are expanding into China, but we're looking at expanding these into the United States. It's funny because in expanding countries, that's where they're buying all the new screens. Here, we've got screens that are 10 years old. Everybody's happy. They don't want to buy new screens. So we're working on expanding them here in the United States as well. So if you start in 2005 with the first Z-screen absorptive system that we had, and you start looking over the years, what you see is we've been increasing light levels. For us, light levels are key. We want bright 3D. I think that that's the thing that's missing in 3D and has been hurting 3D is that the light levels have been too low. And that is really killer. You will watch a movie and you're seeing, half a foot Lambert trickle out onto the screen. You're not going to have a good 3D experience. You're not going to have a good movie experience, period. So we've been working very hard to have those light levels go up in an economically efficient way so that movie theaters, who are mostly funded by popcorn, can actually afford this equipment. So we've been working on brighter and cleaner exhibition, but on the other side of it, we're working on what happens when people are creating movies. So what happens when we're shooting movies, and how does that affect the stereo experience? And this is a place that we found a significant problem. So I'm going to talk about one of our products. It's really a different way of shooting. It's called TrueMotion. And what we're going after is judder. So what's judder? Well, it's always a question. And to answer that question, we have to go back to 1895. So in 1895, we built our little house of motion imaging. We had the very first movie cameras, the very first projection. Everything was great. The little sun shone down on our little house. Everything was really nice. But we had a problem at that time. There was a mathematical problem with the way the camera was rendering motion, the way the camera was capturing motion. And that problem caused judder, a little foundational mathematical problem with our camera. But we've been adding on to it since then. It wasn't a problem then, it was great, but we've been adding on. We've added high frame rate, we've added 4K, we've added stereo imaging, we've added high dynamic range onto our system over the last 100 years. And suddenly we're now talking about judder in the cinema world in a way we never did before. So we were fine with it for a long time. We made Casablanca, we made Star Wars, everything was great. It was always there, but now there's a lot more stress on the way our camera is working. The camera is working. So what do I mean when I say the camera? Well, here's something kind of obvious. Here's a motion imaging system. We have a camera on one end, projector on the other. The job of the camera is to take real continuous, real-world motion that's nice and continuous and smooth, that is not broken into frames, and its job is to break it up into frames. To chop it up into discrete frames that it can then pass over to the projector, whose job is to take those individual frames and put them all back together to try to recreate real, continuous, smooth motion, what happened in the real world. So each part has its job. And when I say that the camera is not doing its job right, and I say it's got a problem, I say that's called judder. To you guys, I will say that is temporal sampling aliasing. So we have sampling aliasing at the camera side. And on the projector, its job is to reconstruct the sampled signal. And if it doesn't do it right, it's called in the industry strobing. I call it temporal reconstruction aliasing. So there are two things, and if you know sampling theory, you know that these two things are actually completely independent of each other. That sampling aliasing and reconstruction aliasing are two separate effects, and you can't fix one and the other. They are actually independent. And the truth is, in digital projection, strobing's pretty good. There is still some temporal reconstruction aliasing as you go instantaneously from frame to frame, but it's not like it was in film projection, where you had these black periods between frames and you had a fairly bad reconstruction filter, effectively. This judder's job was the reconstruction filter. When I talk to marketing people, I don't use these words because they get all kind of queasy feeling when I do. So on the camera side, temporal sampling aliasing is a real problem, and it's always been the same. And when we made digital cameras, we very exactly reproduced the way the shutter was working in film cameras, which is that it was open for half the frame time and closed for half the frame time. So you have a shutter that's it's closed, then instantaneously opens, starts, you integrate, and bam, you're closed. That's a square wave integration that's happening at the camera. That causes a lot of trouble, especially since our frame rate is not very high. It's only 24 frames per second. And that may change, but it's not changing real fast because of reasons. So in the between, you have the frame rate that controls the bandwidth of the system. Frame rate is actually not the thing that fixes judder. Frame rate can fix strobing to a large degree, but it has a very nonlinear relationship with sampling aliasing. And in fact, it's weird. If you crank the frame rate up, you can actually see more judder in many cases because it starts to move those judder frequencies into things that are more apparent to us. Aliasing is weird that way. It's very nonlinear, and it wraps things around. So let's look at a piece of footage. So we have this footage, and if we look at just one frame of this, from this high frame rate shot footage. I'm just going to look at one line of this, one row of pixels, as we run through this piece, and I plot that out. So I call this a sinogram. I have now frames this way, so time is now vertical, and our horizontal resolution is horizontal here still. And what we can look at is we can look at what is going on at these edges as these dancers moved around. And that's interesting to look at. If you look down here in this lower corner, this is what a standard movie camera does and has done for 100 years. This is judder. Now you can see it, because that's aliasing, and we know what aliasing looks like. That's sampling aliasing. The real motion was like this, but it's been chopped up into this really blocky looking thing, and that's what happened when it turned into 24 frames per second. Over here, if we synthesize a different shutter, if we did a better downsample from this high frame rate, we can have something that's much more smooth and more accurate. If you do a really bad job, this is like what your GoPro might do, you have something that's really, really choppy and very broken. That's a way of looking at judder. That's what we care about. In 3D, in stereo imaging, judder is a much more serious problem because it will tend to break down the fusion that the viewer is trying to do. So you're trying to watch something happen, it's nice and fast, everything's going on, superheroes are fighting, and suddenly you can't tell what's in front and what's back, and you get this headache. Judder is a serious noise artifact that can cause a lot of problems with trying to fuse stereo imaging. So what do? Well, we do what I just said. It's very, very simple. You shoot at a high frame rate and we downsample it. It's that easy. Well, it's almost that easy. So most movie cameras are capable of shooting at 120 frames per second or better at full quality. And then we go through and we can take the raw data out of cameras. The workflow for cinema cameras is sort of interesting. We usually do have access to fairly raw data, direct pixel information or direct sensor information on the camera. And then we can drop it to 24 and edit and post just like normal. So we're still delivering 24 frame per second footage. It just looks better. It just flows more accurately. And we're doing a weighted average for all of you. We're doing a finite impulse response filter. We're not very sophisticated in the movie industry, so don't rush us here. We're doing FIR filters, and we're happy about this. And we have software that does this. There have been movies that have been produced using this. Billy Lynn's Long Halftime Walk was shot at 120 frames per second and presented stereoscopically at 120 frames per second in 2 theaters in this country. Everywhere else it was presented at 24 using this process, using TrueMotion. And the 60 Blu-ray, which is beautiful, was also rendered out from the 120 using this process. So let me show you some footage. Enough of this. We will look at footage, and this footage was shot stereoscopically with dual RA Alexa cameras at 120 frames per second, and we did very high dynamic range during this shoot. So let's go ahead and run this little piece. You will need 3D glasses. Now, I will tell you that your standard polarized 3D glasses will work, but I will wear my Stormtrooper glasses, which are much better. So we call this piece our explication piece. So I'm going to go through and tell you, scene by scene, how TrueMotion was used to make this look better. So we'll start with something kind of straightforward. We'll start with this water spray. And that was before, and this is after. Now this is going to be a little subtle, so we're going to do this again. So let's look at this. She walks out with this water spraying back, and we'll stop it right there. And you can see what we're doing is the TrueMotion version is wiped across. We're changing motion blur. That's all we're doing. We're changing motion blur into something that's more realistic. So in the real world, water doesn't look like that when it sprays. It's not little dashy lines, and that's not what you see. What you see is something that's more fluid and will play frame to frame more accurately. And that's what we have done with TrueMotion, is make something that is much more accurate. So here's again normal at regular speed. And this is with TrueMotion. So everything you're seeing here is 24 frames per second, stereoscopic, just like you'd see in a movie theater. So let's play with something. This is my only 2D piece from here. This is rotary motion. So one of the things that we like to see, one of the artifacts of judder is the wagon wheel effect. Judder is the sole cause of the wagon wheel effect. So what we see is that we get rid of the wagon wheel effect if we do this right. So here, let's look at this before. So as that engine starts, we can see some kind of weird forward and backwards motion that's happening in it. And with true motion, it turns into a nice, completely solid spinning disc, as it does in real life. So you can see the side-by-side here. You can see that as the engine speed changes, that the prop looks like it's going kind of forwards and backwards, doing all kinds of crazy things. That's the wagon wheel effect. Now, fixing the wagon wheel effect is probably not the most important thing that we do. It's not a particularly objectionable feature, but it's really important to me because it shows that the math is right. If you fix this, you'll fix that wagon wheel effect. So the wagon wheel effect is not a frame rate problem so much as it's a low-pass filter problem. Other thing we can do, since we've got high frame rate footage, we can do a speed ramp. Now, if you had 24 frames per second footage of her walking towards us, you wouldn't be able to slow her action down very well. But we have access to the original footage, so high frame rate footage, so we can slow her action down without it looking choppy. So this is what normally happens if you double print this. So just repeat frames twice, it'll look very choppy. And this is what we can achieve. Now, there are other algorithms that do this. Optical flow algorithms and things like this can do kind of a nice soft speed ramp, but they have a lot of problems with some of this detail out in the edge of the hair, and her hands will have a lot, anything including optical flow algorithms have a hard time with. So this doesn't making anything up, this is a very straightforward operation, and we can keep shutter constant during that entire speed ramp, which is a pretty neat trick. It's something that you couldn't do in film cameras. So here we have some high contrast things in the background. We have these windows in the background, and we have some strings of lights in the background, and they're very distracting as things go by, especially if you're on a 70-foot screen. If you have these kind of high contrast things in the background going past, it will be distracting from the foreground elements. This is something that cinematographers usually shoot around. They would not have shot this scene this way. I worked with a cinematographer on this, and he said, I would never do this scene this quickly. It would hurt too much. But because we have access to this high frame rate data, and we can smooth this background, we can make this all work a lot more smoothly. So we're looking at the cape that's more smooth, and these lights and these windows that are in the background. So that's what it plays like with kind of a medium setting. Because the frame rate's very low that we're working with, 24 frames per second is well within the human visual perception, because we can see up to 60 hertz, which means 120 frames per second at least. So 24 is a very, very low frequency for us. It means that you want to play with these settings quite a lot to get something that looks right as you're, and looks right is completely an aesthetic call. There's no math I've got to tell you what looks right. It's going to be up to the cinematographer and the colorists to decide what they want. But yeah, you can see what we're doing to the motion blur. And we can go even softer and make something that's very, very soft. We can get rid of all of the judder, and I'll show you what that looks like later. And what you'll find is you have to leave some judder in. If you get rid of all of it, it will look weird. It will look smeary. Not exactly soap opera, that's on the other side of things. But that's what the TVs do. We don't want that either. And when I say normal shutter here, what I refer to is 180-degree shutter. That's a square wave shutter that's half the frame time of the, so it's a 48th of a second is what that would be. But it would be a square wave shutter in our case. So what we're using is this finite, the FIR kernel, so I'll say to you. So the FIR kernel shape we call the synthetic shutter, only because that's turning it into a terminology that cinematographers understand. They understand what shutters do. If you make a shutter wider or narrower, what that does to the look of things. And we're saying, well, now we have shutters that aren't just wider or narrower, but actually fade in and fade out. This is something that's kind of fun. Here we had a sharp and glossy rendering of this action, and the director looked at it and he says, I love the glossy rendering on her dress and hair, but I can't see her eyes, and flamenco's about the eyes, he said. So we simply render this out with two different shutter waveforms. And then in the edit package in DaVinci Resolve, we window on her face, and we apply the crisper shutter on her face, the more juddery shutter on her face, and the softer shutter everywhere else. And this gives us a really beautiful composited look. And if you don't think that movie makers obsess about these sorts of things, then you have not met movie makers. They'll fiddle around for days on the color of the dress. So this is the sort of composite that we can put together. So this is before, and that's composited. And in 3D, this plays really well. We have a beautiful motion on her dress and hair, something that flows very nicely and doesn't break the stereoscopic effect that we're really going for. So this is ours. Yeah, we had mixed in there one that was not. So let's put a few of these techniques together. So we had this shot, and we were very happy to get this shot towards the end of the day, but the airplane is just going by too fast. So we've been chasing her around with a truck all day, and we get the shot, and the airplane goes by too fast. And we want to slow it down for the edit. But if we do that by repeating frames from a 24 frame per second original, it's going to look really choppy, and that will not be acceptable for viewing. But like I showed you before, we have access to the high frame rate footage. So we can slow that airplane down and speed it back up, keeping effective shutter constant for that entire period and exposure essentially constant over that period. And we can have something that looks fairly natural, as if the airplane's just kind of hanging up there as it's going across. But you see what happens when we do that. We now have the wagon wheel effect. So as we run to fewer and fewer frames that are being used for each output frame, our shutter is too narrow for those spokes. That's very simple. We just render it with a wider shutter waveform. But we don't want to use that on the top of the screen because that will make the airplane too soft looking, and we want to keep the nice contrast on that airplane. So we do the same thing we just did with the lady who was dancing. We can split this between top and bottom of the screen and have one shutter setting for the bottom of the screen and a different shutter setting for the top. Do our speed ramp all the way through. We don't have any distracting spokes. We have something that looks exactly the way we want it to. And then she smiles at the end as we go off screen because she knows we finally got the shot. We had a whole van full of crew. They all cheered on the radio all at the same time. It's always fun to do things in camera. So what I'll show you now is the kind of full spectrum of what we can do. And so what this is showing is starting with, this is what happens if you get rid of all judder. There is no judder in this shot. And it is pretty smeary. So if you get rid of everything, mathematically get rid of all sampling aliasing, which you can do, you've got something that looks like this, that's just lost so much contrast that it's not really much fun to watch. It's pretty smeary. And so we go to something that's just soft. So we'll make this just a little sharper. This allows a little bit of judder in, but not much. And it's still pretty soft, a little bit dreamy looking. That's better. Now we're going to add a little more contrast in. What we've actually added in is some negative lobes on this. So you'll see there's a little bit of darkening around bright edges that's happening here. That's a choice that cinematographers can make or not, is whether they'd like to allow some negative lobes. You can get better contrast response if you do allow some in. Anybody who's done Lanczos or bicubic resampling knows that the negatives can help you. They can also kill you. And so this is what we like. That's actually kind of the look that we thought was really pretty for our piece. Here's a synthesized 180-degree shutter. So this is what it looks like in a normal camera. So this is what we've seen for 100 years. It's not terrible. This is how we watch movies. But it's not quite what we wanted for this. But you can start to feel the choppiness as they're moving past each other. And then I'll take it to an extreme here. I will go to a 45-degree or 72-degree square wave shutter. This is what I call the GoPro in sunlight look. A lot of cameras, a lot of consumer cameras, of course, control exposure by reducing the shutter time. And so that can give you outdoors an extremely staccato look. They're introducing an awful lot. It's basically a stop motion look is what you really have. Stop motion being a 0-degree shutter effectively from a motion standpoint. And that could be a nice look. A lot of action sequences like that really staccato look. But if you shot it that way, you would have no recourse later on. If you decide later, oh, I didn't really want that sharp look, that's too much, it's baked in. If you shoot at a high frame rate, you have so much more flexibility to do whatever you want, to deliver to different output frame rates and do all kinds of different things. And it really does make life a lot easier. Good deal. Okay, so we're going to now show our little 5-minute piece that we did using this, and you can see how this all went together. She was a lot of fun. Both of the dancers are extremely talented. So I will talk about one more thing, and I'll take some questions in. So our last thing that I want to talk to you about is our denoising software, which we call True Image. So noise is also a particular problem in stereo imaging. And this is something that noise, as you know, is always with us. Noise that we see in cinema cameras these days is not electronic noise. It's not caused by bad cinema cameras. It's caused by the fact that the real world is just made of noise. Photon statistic noise is the thing. So when you're imaging a scene, you only have so many photons, and even if you count them up exactly precisely, you're still going to have a noisy image. And but that's not okay from a 3D standpoint. A lot of times that noise will cause a great deal of viewer fatigue and discomfort. And so what we have in True Image is something that is pretty outstanding. It is a fairly deep analysis piece of software. It takes all the computers to run this. Our frame rate on this thing is nothing to be excited about. Our frame rate on a single computer is something like 5 to 10 minutes per frame. So this runs on Amazon Cloud Services. So when we do a full movie through True Image, we take a lot of computers out of the Amazon Cloud and sit there and process that movie. And what it's doing is it's doing a forwards and backwards in time analysis, a motion tracking analysis, a color analysis, a left to right analysis, and it's putting all of that together to try to reconstruct what was the original objects that were in that scene. And it does a really good job at this. It's fairly, I say it's easy to use. It is easy to use. It's hard on the computers, but that's not us. That's somebody else. And if you throw, we say near real-time image correction. I did not make this slide. I always laugh at that. I was like, yeah, with 1,000 computers, it's near real-time. And it leverages latest processing out. So it's really good. We've been using this for a lot of years. Let's look. This is a blue channel of a cinema camera. This is in a real actual movie. This is what the blue channel looked like. And blue it's mean to use the blue channel because blue is where we have the fewest photons, but that's what's going on there. That's what True Image did with that frame. So let me show you that in live a little bit here. So we're going to run the next 3D clip here. This one's fairly short. So the 3D glass is on for this. So this is from the movie The Hobbit, and this is what we had originally when Peter Jackson came to us with this problem. And you can see what's going on in the blue channel. So the blue channel has got a lot of noise, and it is, you watch a 2-hour, 2.5-hour, 3-hour movie, and this is going to be very fatiguing. And so this is what True Image does with that blue channel. So this is before. Now let's zoom in, and we want to see what can we do with detail. This is before, and this is after. And you can see that we really are preserving, we're actually restoring a lot of detail that was very difficult to see before. And we can see a little bit of smoke curling up. We have nice sharp edges. We have soft detail. And as we look at that in full color, we can see that this becomes a lot easier to watch, especially as you get to a big screen. Now, if you look in the background, the problem with noise in 3D becomes apparent. You have what looks like a veil hanging through the middle of your scene. So you have all this noise there, and your eye can't localize what's going on. So you have a really hard time fusing this image if there's this weird veil of noise hanging throughout. So this is before and then with True Image. And this is before the original. So you can see sort of a veil hanging through the middle of the scene. So this is used by filmmakers now. It's used sometimes in problem shots, but increasingly people are looking at using it end to end through the entire production. Okay, that's my little piece there. So that is our technology from end to end. That's what we've been working on. We really do believe that the future of 3D is, as we like to say, the future of 3D is bright. We are trying to make it brighter. And that's what we've been working on. And again, we really do, as a company and as a cinema industry, have a lot to thank the people in this room for. And I thank you very much for all your work over the last 30 years. You've really made this wonderful for everyone.